Hello everyone, I am Assistant Professor Shendge Swapnil Sampatrao, Head of Department of Physics, KAA NMS, Arts, Commerce and Science College, Satana, Nashik. So student, today we are going to learn about the Gauss law. So what is meant by Gauss law? Here in this slide, it is shown that this is the expression for the Gauss law, that is the closed integral E bar dot ds bar is equal to q enclosed upon epsilon naught. So this is the formula for the Gauss law. In this slide we have given the Gaussian surface. The Gaussian surface is known as a closed surface in three-dimensional space such that the flux of a vector field is calculated. These vector fields can either be the gravitational field or the electrical field or the magnetic field. Here some properties of the Gaussian surface are given, which are such as the Gaussian surface should be chosen such a way that the magnitude of electric field is either uniform or zero at every point on the surface. The second property is the Gaussian surface should be chosen in such a way that the every point on the surface of the electric field is either parallel or perpendicular to the surface. Here are some applications of Gauss law. There are so many applications which are depending on the shape of the distribution charge area. Though here the first application is that the electric field intensity due to spherical charge distribution. Non-conducting sphere of radius r and charge is uniformly distributed over the surface of the area. This is the condition for the electric field intensity due to spherical charge distribution. Here by using Gauss law we can show that electric field intensity inside the sphere, that is the r is less than capital R. So here small r is nothing but the charge radius and capital R is the radius of the sphere. So here E inside, that is electric field intensity inside, is equal to 0. Second is electric field intensity on the surface of the sphere, that is R equal to capital R, that is Gaussian surface is equal to the Gaussian surface radius is equal to the radius of sphere. So E on, that is nothing but the electric field intensity on the surface, that means E on is equal to 1 upon 4 pi epsilon naught into q upon r square. Third type is that electric field intensity outside the surface of the sphere, that is the Gaussian surface radius is greater than the radius of the sphere, that is small r is greater than capital R. So E out means electric field intensity outside of the surface. So E out is equal to 1 upon 4 pi epsilon naught into q upon small r square. Small r, again I am mentioning that the small r is nothing but the radius of Gaussian surface. Okay. Another application of Gauss law, which is depending on the electric field intensity due to long charged wire. So in this figure there is a long charge wire here, and the Gaussian surface is surrounding this charged wire as mentioned in this diagram. So here is lambda. Lambda is nothing but the uniform line charge density, which is indicated by lambda symbol. Capital R is nothing but the radius of Gaussian surface which is along with the wire. E is nothing but the electric field intensity, and L is nothing but the Gaussian surface cylindrical shaped length. Okay. So electric field intensity due to long charged wire is equal to lambda upon 2 pi epsilon r, epsilon naught r, where lambda is the uniform line charge density, that is coulomb per meter. Another application of Gauss law, which is depending on the electric field intensity due to a spherical charge distribution. Here the spherical charge distribution in non-conducting sphere of radius capital R, and charge is uniformly distributed throughout the volume of the sphere. Okay, so here in this figure, E inside is mentioned here. E is nothing but electric field intensity, and it is a positively charged located over this in this sphere here. Okay, so electric field intensity at a distance r from the center of the sphere is E in. E in means electric field intensity inside. So E in is equal to rho r upon 3 times epsilon naught, where rho is the uniform volume charge density. Okay. So another application of Gauss law is electric field intensity due to uniformly charged non-conducting solid cylinder of radius capital R and the uniform volume charge density rho. Again I am mentioning that the electric field intensity due to uniformly charged non-conducting solid cylinder of radius R, non-conducting solid cylinder of radius R, and the uniform volume charge density rho. So again here there are 3 types. So in this figure the non-conducting solid cylinder is shown by the yellow color which has the radius capital R. Okay, the Gaussian surface is shown by the small r, and a rho indicates that the volume charge density here. So the electric field intensity at a distance small r is greater than capital R. That means Gaussian surface cylinder radius is greater than the solid cylinder radius. Okay, so the electric field intensity at a distance small r is greater than capital R from the axis of the cylinder. That means outside the cylinder is E is equal to rho r square upon 2 epsilon naught r. Second application or second formula for the electric field intensity at a distance r from the axis of cylinder on the surface of the cylinder is, that means here small r is equal to capital R. So it is given by E is equal to rho r upon 2 epsilon naught r. The electric field intensity at a distance small r is less than capital R. That means the Gaussian surface of the cylinder has the radius smaller than the solid cylinder radius from the axis of the cylinder. Okay, so the electric field intensity at a distance small r is less than capital R from the axis of the cylinder inside the cylinder is E is equal to rho r upon 2 epsilon naught. Okay, another application of Gauss law is the electric field intensity due to non-conducting uniformly charged sheet. Okay, so in this diagram there is a charge sheet with uniformly charged infinite plane sheet here mentioned. Delta S, that is nothing but the surface here mentioned. Cylindrical Gaussian surface is also shown in this field cylinder. Here two way electric field intensity mentioned here. Okay, so the electric field intensity just outside the uniformly charged conducting infinite plane sheet of electrical charges is given by E is equal to sigma upon 2 epsilon naught, where sigma is the surface charge density. That means it is a two-dimensional density, that is sigma indicates that the sigma is the surface charge density and its unit is coulomb per meter square. Another form of Gauss law is We have already seen these forms, that is nothing but the closed integral form. We have the integral form. Gauss law is closed integral E bar dot ds bar is equal to q enclosed upon epsilon naught. By using the Gauss divergence theorem, we can write closed integral E bar dot ds bar is equal to closed integral del dot E bar into dv. That means here surface integral is converted into volume integral, and by using the definition of volume charge density, q is equal to closed integral rho dv. So here by using above value, equation 1 becomes, because we have to mention here q, so equation 1 becomes closed integral del dot E bar. So dv is equal to 1 upon epsilon naught closed integral rho dv. So by comparing the integrands, we can write del dot E bar is equal to rho upon epsilon naught, and it can be denoted by equation number 2. So equation 2 represents differential form of Gauss law. In this way, we have another form of Gauss law is seen in this equation number 2. So another differential form of Gauss law, the differential form of Gauss law del dot E bar is equal to rho upon epsilon naught. It is particularly applicable to derive Laplace and Poisson's equation, that is del square V is and equal to 0 and del square V is equal to minus rho upon epsilon naught respectively, which are used to find the form of potential where the particular boundary condition are imposed. Here again differential form of Gauss law in dielectrics. So we have the differential form of laws in electrostatics. Del dot E bar is equal to rho upon epsilon naught. Here rho is the volume charge density of free charges. In case of dielectrics, we have to consider bound charges also. Then Gauss law becomes del dot E bar is equal to rho for free and plus rho for bound upon epsilon naught. Here rho free means rho is the volume charge density for free charges, and rho bound means the rho means volume charge density for bound charges. These are the differences. Del dot E bar is equal to rho free plus rho bound upon epsilon naught. By the definition of volume bound charge density and polarization vector, we have rho bound is equal to minus del bar dot P bar. Therefore del bar dot E bar is equal to rho free minus del dot P bar upon epsilon naught. Here we are substituting the values of rho bound, means the volume charge density for the bounded charges. By rearranging these equation, we get del bar dot epsilon naught E bar plus P bar is equal to rho free, that means volume charge density for free charges. But del dot epsilon naught E bar plus P bar is equal to D bar. So therefore V bar dot D bar is equal to rho free. This is the differential form of Gauss law in dielectrics, where rho free is equal to P bar dot unit vector n cap. So here note that electric displacement vector, that is mean D bar, is connected with the free charge only, so it is not altered by the introduction of dielectrics. Electric polarization vector P bar is connected with the bound charges, that means induced or polarization charges. Electric field intensity vector E bar is connected with both bound and free charges. Here is the basic and integral form of the Gauss law, which is already we have discussed. Integral form of the Gauss law, that means the statement, the closed surface integral of electric field intensity is equal to the charge enclosed by the surface times 1 upon epsilon naught. So closed surface integral here E bar dot ds bar is equal to q enclosed epsilon naught. Physically, epsilon closed integral E bar dot ds bar represents the electric flux through the closed surface due to the enclosed charges. If the charge distribution is not enclosed, then we have to consider the imaginary surface called as Gaussian surface, and the integral phi closed integral E bar dot ds bar is to be carried over this surface. Okay, so in this way we have discussed the Gauss law. Lastly we have to discuss Gauss law in dielectrics integral form. The Gauss law in dielectrics can be stated as the surface integral of displacement vector d bar over a closed surface is equal to the free charges enclosed within the surface, that is the d bar dot ds bar is equal to q enclosed, where q enclosed is the total free charge inside the surface. So here this format shows the charge distribution. Here there are again two types, one is uniform charge distribution and another is non-uniform charge distribution. In uniform charge distribution, the first point for the line charge means one dimensional distribution. Here lambda is equal to constant, q is equal to lambda L, q enclosed is equal to lambda into L enclosed. For surface charge distribution, that means for 2D, sigma is equal to constant, q is equal to sigma into A, q enclosed is equal to sigma A into enclosed. Another is for volume charge distribution, that means for 3D, rho is equal to constant, q is equal to rho into V, q enclosed is equal to rho volume enclosed. For non-uniform distribution, charge distribution, that means for line charge distribution where the charge distribution is non-uniform, so lambda is not constant, therefore q enclosed is equal to integral lambda into dl. Another for surface charge distribution, that means non-uniform charge distribution for two-dimensional, sigma is not constant, so q enclosed is equal to integral sigma dA. Third, for volume charge non-uniform distribution, rho is not constant, so therefore q enclosed is equal to integral rho dV. So in this way we have discussed the charge distribution for uniform and non-uniform phases here. So lastly, thank you.